Ever pondered about the unseen forces that keep us grounded, or the mysteries that space-time holds? Well, brace yourselves for a wild ride into the realm of speculation as we toy with a thought-provoking idea: classical geometric dynamics, or CGD for short. This theory gives us a fresh lens to view the universe, proposing a radical shift in our understanding of gravity. Instead of picturing gravity as a force mediated by elusive particles or quantum fields, CGD paints a different picture. It suggests that the gravitational effects we experience are actually the result of space-time's inherent geometric properties. Picture space-time like an elastic fabric, not a tangible material, but a geometric property that can stretch and rebound. Massive objects like planets or stars create dimples in this fabric, and voila! We have what we perceive as gravity. So, imagine if gravity isn't a force, but an effect of the elasticity of space-time itself. Picture space-time as a stretchy fabric, with every object causing a dimple in its surface. This isn't a physical material, rather a geometric property. Imagine tossing a marble onto a trampoline. The marble would create a dent, right? That's the idea. Objects with mass, like our marble, create these dimples in space-time. Now think about moving along this stretchy surface. You'd naturally be drawn towards the dimples, wouldn't you? That's essentially what gravity is in the classical geometric dynamics theory. It's not so much a force pulling you down, but more of a natural tendency to move towards areas of least resistance, or in our case, the least stressed state of the space-time fabric. In this whimsical view, everything from the apple falling from the tree to the moon orbiting our planet is just a result of us all surfing on the ripples and dimples of this cosmic canvas. But what about the strange world of quantum particles? Well, in the realm of classical geometric dynamics, or CGD, these tiny particles take on a whole new identity. They're not just abstract mathematical entities or quantum fields. Instead, they're envisioned as localized knots or twists in the fabric of space-time. Imagine pulling a thread on your favorite sweater and creating a small, intricate knot. That's essentially what particles are in this theory, little knots in the cosmic fabric. Quantum probabilities, those perplexing chances that govern the behavior of particles, emerge from the complex interplay of these twists and the inherent elasticity of space-time. It's like a cosmic dance, with each knot twisting and twirling in response to the tension and stretch of the space-time fabric. Now, let's talk about black holes. These astronomical enigmas are no longer regions of infinite density or singularities in our CGD theory. Instead, they're areas where the space-time fabric is twisted and knotted so intensely that nothing, not even light, can escape their grip. But instead of an event horizon from which nothing can return, CGD posits a rebound zone where the elastic force of space-time is at its maximum tension. It's like the universe's version of a trampoline, but one you definitely don't want to bounce on. So in CGD, a black hole is a massive knot of space-time twisting reality around it. Can this theory bridge the divide between classical and quantum physics, you may ask? Well, let's take a look. The classical geometric dynamics theory, or CGD, proposes a fascinating perspective, one that treats both gravity and quantum phenomena as emerging from the properties of space-time itself. This perspective eliminates the need for force-carrying particles like gravitons, which have long been a thorn in the side of physicists trying to reconcile the two theories. In the world of CGD, everything from the grand orbits of planets to the unpredictable behavior of subatomic particles is guided by the geometric dynamics of space-time. This means that the divide between classical and quantum physics is not just bridged, but entirely dissolved. It's as if we've been trying to fit a square peg into a round hole, only to realize that there's no hole at all, just an elastic fabric that accommodates any shape. Now, what predictions does CGD make? First, gravitational waves are seen as vibrations or ripples in the elastic fabric of space-time. Imagine throwing a pebble into a pond and watching the ripples spread out. That's gravitational waves for you. Second, at very high energies or tiny scales, space-time's elasticity might exhibit quantized properties, leading to discrete units of space or time. It's like space-time is made of tiny Lego blocks. Lastly, Interactions that seem non-local at the quantum level, like entanglement, are the result of direct connections or threads in the space-time fabric. Imagine two marbles tied together by a string, no matter how far apart they are. A tug on one is felt by the other. In this imaginative journey from the orbits of planets to the behavior of subatomic particles, everything is guided by the geometric dance of space-time.